Okay. Hi, everyone. Thanks for joining. So let's get started. My name is Shuin Sohrabi, and today, together with Octavian Udra and Michael Katz, we'll present a tutorial on AI planning, theory, and practice. Now, just a few things before we get started. If you can, please write down your areas of expertise in the chat so we have some ideas about your background. Also, if you have questions, please use the raise hand feature to ask your questions. Everyone is muted on entry, so please unmute yourself to ask your question and then mute yourself back again. You can also ask your questions in chat, but as we're presenting, we may not get to those questions on time. Also, just letting you know that we are recording this tutorial. And now we do encourage questions throughout the tutorial, so please feel free to interrupt us to ask your questions. Now, before we get started, I want to acknowledge and thank many of our past and present collaborators. A subset of them are shown here. So what is AI planning? Now, AI planning is a long-standing sub-area of AI since the 60s. Planning sits well with autonomous systems and started with robots. And when autonomous systems has to achieve something, it has to plan for it ahead of time. Now, this is a picture of a Shaky, the robot, which was the first mobile robot with the ability to perceive and reason about its surroundings. This was the subject of SRI's Artificial Intelligence Center research from 1966 to 1972. Shaky could perform tasks that required planning, route finding, and rearranging of simple objects. The robot greatly influenced modern robotics and AI techniques. Now, AI planning is about the task of finding a procedure course of action for a declarative described system to reach its goals while optimizing overall performance measures. Now, for realistic domains, the space of possible plans is very large, so optimization is very important. Also important is identifying a good quality plan, in other cases, top quality plan, or even finding a set of possibly ranked plans. So the basic planning problem goes as follows. You're given a description of possible initial state of the board, desired goals, a set of possible actions, and you want to synthesize a plan that's guaranteed to generate a state which contains the desired goals. Now, the simplest example to help ground the basic terminology is the logistic or transportation example. You have your initial state location, you have a set of transportation vehicles, for example, trucks, aircrafts, cars, as well as a set of packages. And you have to deliver these packages, that's your goal state. And what you get as an output of a planner is a sequence of actions that need to take place in order to achieve your goal state. You may also get a set of alternative plans that you want to explore. I want to mention that much has gone into AI planning research, and AI planning is a very active area of research. Now, there are many applications that are examples of use of AI planning, and here there's just 4 such applications at IBM. The left top, this is the healthcare setting where the objective is to help users, in this case, nurses and physicians, in early detection of health complications in the ICU setting. Top right, this is the D3WA system, a goal-directed conversational agent that uses automated planning. Down left, this is the risk management setting, where the objective is to assist financial organizations in identifying and managing emerging risks. Down right is the automated machine learning setting, where the objective is to automatically generate machine learning pipelines. Now, there are many common things between applications. First is the existence of domain knowledge. There are domain experts who can provide the necessary domain knowledge. For example, the type of knowledge for the healthcare setting can be provided by doctors or their books written on the subject. Similarly, for the scenario planning, there could be lots of articles regarding the cause and effects that can be explored. Second, people want more than just one plan, either for explanation purposes or in the case of plan failure, or in general case, they want to have a better sense of what is possible. In some settings, they want to have a diverse set of plans. In some settings, top high quality plans, and in some diverse but bounded quality plans. Third, humans are involved beyond just providing the domain knowledge. We have humans that interact with the tools. They need to validate and like what they see. They need the solution visualized and explainable to them. They can dislike or like some solutions more than the others, and they should have a way of indicating that. And of course, there are challenges as well. Now, modeling is an important aspect of use and adaptation of AI planning. Modeling is about how to drive the planning problem in order to use the planning tools. Theory, how do you compute a solution to the problem? What planning tools to use? In some cases, you want planners that are available out there. And in some cases, you end up creating new planning theory and tools that were motivated by this particular problem that you have or this particular application, but can be used in many other application settings. I'll give examples of those later in the talk. Now, to motivate this talk further, I'll briefly drill down on one application. That is the down left project on scenario planning. Scenario Planning Advisor, or SPA, is a technology that automatically projects many possible future scenarios to provide insights for strategic decision making. So what is scenario planning? Scenario planning is a commonly used enterprise risk management technique facilitating decision makers in formulating long-term plans by considering multiple alternative futures. It's typically a manual, highly labor-intensive process involving dozens of experts and hundreds to thousands of person hours. And as a result, only a few scenarios can be constructed by humans. And of course, bias can also be introduced. So for example, high impact or low likelihood events could potentially be overlooked. So here we developed the tool that's called SPA, which is a mature research asset at IBM Research. This is available as an open service for non-commercial use. The benefit you get is reduction in time for building scenarios from months to hours, and explorations of orders of magnitudes more scenarios than possible if you were to build it manually. And in fact, one of SPA's clients says, and I quote, SPA is 30 times faster in time to generate the dynamic risk model and a scenario, and 3,000 times faster in time to generate the second scenario and each second scenario. And this is in comparison to a human expert. So for the solution, we exploit NLU techniques to semi-automatically construct scenario planning models. And we automatically explore the space of possible scenarios with an AI planner and choose scenarios of high relevance to client at a particular time. So for SPA, but also for many other applications, there are aspects of modeling, aspects of theory, and tooling that needs to be addressed. So why AI planning is important? AI planning applications are everywhere. Many examples are shown in this picture, in this slide. So for example, dialogue, cybersecurity, transportation, logistics, and IT. And many companies have understood the value of AI planning and use it in their offerings. So for example, NASA uses AI planning in Mars rovers. Schlumberger uses AI planning in automating the drilling process, and IBM uses it in many applications. Now note that several of these applications are not your typical classical planning problem with the initial state and goal, but planning is nevertheless used here. And the key there is this transformation or compilation step that enables the use of planning in many of these settings. So how to spot a planning problem? So AI planning can help when your problem can be described in a declarative way, where you have a domain knowledge that shouldn't be ignored, or pure learning techniques are difficult to use either because there's a structure of the problem that cannot be learned by training, or that there is little to no available training data. And you want to be able to explain a particular course of action the system took. You can leverage the existing relationship between a problem that's similar to yours to AI planning. I'll talk more about this in the modeling part of this tutorial. Now, a common framework that we adopt for the use of AI planning is as follows. As I mentioned before, we have domain knowledge, and the first step is to create a planning model. Now, that can be elicited or learned. Hence, we need to somehow address the modeling challenge, which is any gap between identifying that you have a planning problem at hand, that you can use a planner to compute a solution, to specifying a planning problem in a language such as PDDL or planning domain definition language, in order to use a planner to compute a solution to the original problem. Then we need to run the appropriate planner to solve it, find plans, sometimes lots of plans. Sometimes we need to create planners that are suitable for our task and are motivated by the problem we face. In fact, we've worked on a number of different planners such as top K planning, top quality planning, or
becoming a growing concern. And it's not only
diverse
us,
planning.
but also like...
Can somebody please go on mute? Michael, Octavian, can you? Thank you. So now all of these are motivated by the applications we face, and yet they're not domain dependent. That is, we made these planners available and the tools can be used by others. Then we need to do post-processing to translate the solution for the problem of interest and inspect the solution. And this can be done by the users of the application, which can be different from the domain experts. And oftentimes you may need to adjust the model through feedback and start again. And one of the things you get for free with AI planning is that plans are very much accessible and understandable by humans with perhaps just a good UI interface. So once the users view the plan, they can give feedback to the system and the models can be adjusted accordingly. So naturally, here's the agenda for this tutorial. First, Michael will talk about the theory and planning tools. Then I will talk about the modeling challenge. And then Octavian will cover the tools and applications. And I would like to mention that Octavian will run a hands-on session that will cover the end-to-end use of AI planning within the automated pipeline generation applications. All right. I'm now going to hand it over to Michael, but at this point, if you have any questions, please feel free to ask them.
Okay, so let me start sharing. Okay, can you see my slides?
Yes, we can. We are all good.
Great. Sec. Let me just set everything up here. Okay, okay, my name is Michael Katz. I will do this part, and in this part, I will give a concise introduction into the theory of AI planning. I cannot stress enough that this is a very restricted view, and this is a restricted view of a small part of the field and the research that was done in that field over the years. So don't take these slides as like everything that was done in planning. It's far, far from it. Okay, so please feel free to stop me at any point, ask questions. I would like this tutorial to be as interactive as possible. And as Shirin said, just use the raise hand feature, and I should be able to see it on my other monitor. Okay, so, and no, it doesn't move. Okay, so what is planning? To quote a colleague, planning is the art and practice of thinking before acting, to be able to choose a course of action that is most beneficial to achieve your goals. So planning is essentially about selecting an action in the current situation, in other words, locally, that is most beneficial for you globally. And there are many areas of computer science in general and AI in particular that deal with similar problems. The existing approaches can be roughly partitioned into three main categories. One is specifying the control programmatically. Another one is to learn the control from experience, and we have seen a lot of work on that over the last years. And the third one is deriving the control automatically from a declarative model. So planning belongs to the third category, and it deals with producing the behavior from the model by solving the model. So we can say that planning is a model-based approach to action selection. You might have heard of other model-based approaches in computer science, such as Boolean satisfiability, constraint satisfaction or optimization, answer set programming, mixed integer programming, and others. The rest of my talk is dedicated to answering two questions. First one is, what is the planning model? And the second one is, how do we solve it? So let's start with the first one. What is the planning model? Well, there are actually several planning models. Let's start with the simplest one, which has also received probably the most attention over the course of the more than 50 years of research on planning. So classical planning model is a tuple of the following 6 elements. First, a finite set of states S. One of these states is called the initial state. Some non-empty subset of these states are called goal states. Next, we have a finite set of actions with a subset of applicable actions identified for each state. A deterministic transition function maps a state and an applicable action into a resultant state. Finally, each transition has an associated non-negative action cost. So far, so good? Okay, let's move on. So solutions to the classical planning models are sequences of applicable actions that start at the initial state and end at some goal state. Pretty easy. Going beyond classical planning, relaxing the assumptions marked in blue here results in more general models, such as planning with preferences of soft goals, when the hard goals are the assumption is relaxed. Right? Conformant and contingent planning deal with partial knowledge about the initial state. So if you don't have known single initial state, you can have multiple possible initial states, or you can have a belief over the initial states. Relaxing the assumptions on deterministic action outcomes will result in non-deterministic or probabilistic planning. Relaxing the assumption of observability in general takes us into a realm of partial observable planning. In order to be able to completely represent the models, we use a planning language. Probably the simplest and the most commonly known is STRIPS, which stands for Stanford Research Institute Problem Solving. In STRIPS, the planning problem is given as a tuple of atoms, a finite set of Boolean variables, operators, each described by the triple of preconditions, add effects and delete effects, each of which is a subset of atoms. Each operator has an associated non-negative cost. An initial state is then a subset of atoms, and so is a goal description. Another well-known planning language is called SAS+, often also referred as FDR or finite domain representation. While very similar to STRIPS, FDR operates over multi-valued variables instead of Boolean ones. Each variable can be assigned one of these values at a time. An assignment of a value to some subset of variables is called a partial variable assignment. The operators are then defined by two partial variable assignments called preconditions and effects. The initial state is a full variable assignment, and the goal is a partial variable assignment. In both STRIPS and FDR, a plan is a sequence of actions mapping the initial state into some state that is consistent with G. In order to define that, we need to understand what it means to map a state to another state and what it means to be consistent with G. In other words, we need to show how language determines a model. So given a STRIPS or FDR planning task, we can define a model as follows. Let's focus on STRIPS here. Right? So the states are all subsets of F. The initial state is exactly the subset I. The goal states are all states that are supersets of G. The actions applicable in S are those whose preconditions is a subset of S. The state resulting from applying an action A in S is obtained by removing the delete effects of A and then adding its add effects. The transition costs are then corresponding to action costs. Solutions to the models are plans for the planning tasks and vice versa. By now, you must be wondering what is the connection between planning and the field that has received a lot of attention in the recent years, reinforcement learning, specifically model-based reinforcement learning. While planning and RL were developed separately, there is a tight connection between the two fields. In what follows, I will show how a STRIPS planning task can be used to define the commonly used models in RL. For the forward model, we need to define the next state, given the current state in an action. This is done the same way as in the planning model, with the difference that non-applicable actions map a state to itself. For backward model, we regress an action in a state by removing add effects and adding preconditions. This is only valid for actions whose delete effects don't appear in the state. For inverse model, we need to find an action whose preconditions are included in the state as I, and applying which would result in the next state as I plus 1. The rewards approximate the negative of the true optimal cost of reaching the goal from the state. And the transition rewards can then be approximated by a difference between the cost estimates for the two states. In what follows, we will talk about cost estimates in planning and ways to automatically compute informative estimates. For the sake of simplicity, I will not talk here about the non-deterministic setting. Clearly, a more informative model is a mixed blessing. It is not easy to obtain, as you will see in the next part of this tutorial. However, it clearly pays off to have it. And in the next slides, I will show what can be done when you actually have the planning model. Okay, having established the model, we can think about the questions that we might want to ask about the model or the computational problems that we want to solve. The first one is called cost optimal planning, the problem of finding a sequence of actions or a plan that minimizes the summed action cost. Next, in satisficing planning, we want to find any plan, improving the plan cost as much as possible. In agile planning, we care only about how quickly a plan can be found. Top K planning generalizes cost optimal planning, requiring to find K plans of top cost. Top quality searches for all plans, possibly model some equivalence criteria, up to a certain cost bound. Diverse planning deals with both plan quality and pairwise diversity, defining a variety of computational problems, considering satisfying bounded or optimal solutions on any of the two axes.
Michael,
going beyond the classical. Sorry, yeah.
Michael, hi, Biplav here. Can I ask a quick question here?
Of course.
Yeah. My question is, how do you see anytime planning or anytime algorithms in this kind of setup?
Oh yeah, it's a completely different setup, right? As I mentioned before, here you kind of locally make a decision, but you have a global view in mind, right? In anytime planning, you usually don't consider yourself as a global view, right?
Okay.
But yeah, so if you have the model, you can do many things, right? But usually in anytime planning, you don't, or
Okay.
you only have a partial model.
Okay, the source of the confusion is agile planning. So just for everyone's benefit, anytime planning means that at any given time you have a working plan or a solution which you iteratively improve. And
right,
so,
no, but in agile planning you need to have a feasible plan.
Okay,
that's
why my question. What's the difference?
Right.
Okay.
Yeah, so in agile planning, what you just don't care about, it's like satisfying planning, but you don't really care about the cost. You just want to find a plan, a valid plan, as quickly as possible.
Thank you.
So, okay, so going beyond the classical planning model, net benefit planning considers both the cost of a plan and the utility obtained by the plan. And we aim at finding a plan that maximizes the difference between the two values. In oversubscription planning, you also deal with costs and utilities, but we don't make the assumption that these two are comparable. So plans will have a bounded cost, and the aim is to find such a plan maximizes its utility. In conformal planning, we do not know the precise initial state, having instead a set of possible initial states. The aim is to find a single plan that would work no matter which of these possible initial states was the right one. In contingent planning, we have the same setting of multiple possible initial states, but we do not need a single linear sequence of actions to work in all states, and we allow for conditional branching. In temporal planning, actions have durations. We need to find both the actions to perform and their schedule. In probabilistic planning, a solution is a policy mapping states to actions, optimizing one of the possible objectives, either expected total rewards over the finite horizon, or expected average rewards over an infinite horizon, or expected discounted rewards over an infinite horizon. In the following slides, I will mostly focus on classical planning, and this setting is complex enough. So why is planning difficult? So So now that we have defined the computational problems, we need to ask ourselves how difficult these problems really are. Plans correspond to paths in the transition graph of the planning problem. And we all know that finding even an optimal path in a graph can be done efficiently in polynomial time. But polynomial in what? The typical number of nodes in the transition graph is huge, and constructing it is not feasible in practice, even for relatively small problems. Planning algorithms work with the planning task representation in strips or SAS class and measure the complexity in terms of that representation size. Note that the transition graph size is exponential in the size of the strips or SAS class representation. Even for the simplest computational problem of agile classical strips planning, the complexity is piece-space complete. This is due to the fact that the plans can be exponentially long. Think of towers of Hanoi, for example. Planning algorithms are able to solve these problems efficiently because they avoid constructing the entire transition graph. We will talk more about how this can be done in the next slides. Having established what planning problems are, let's look at the methods developed over the years for solving these problems. As I mentioned before, we focus here on classical planning. So the first algorithm was the strips algorithm, which keeps the stack of closed facts, finds an action that achieves the top fact in the stack, removes it, and adds the preconditions of that action instead. Partial ordered causal link planning performs a search in the space of partial plans. Graph plan constructs a graph in a forward manner that encodes all possible parallel plans up to a given bound, and then performs a backward search in the constructed graph. SAT plan takes a slightly different approach. Setting a bound on the plan length makes planning NP complete. Then it can be cast as a different computational problem, for example, Boolean satisfiability. SAT solvers can then be used to solve the new problem. The last two approaches I will mention are currently the best performing ones. First, informed search, also known as heuristic search, performs a forward search in the state space, starting from the initial state, ordering search nodes with the help of cost to go estimates H. The search stops when a goal state was found. These estimates are automatically extracted from the planning task description. A large portion of the research focus is dedicated to finding ways of extracting informative cost to go estimates automatically. Since a typical search could explore billions of nodes, these estimates need not only be informative, but also computationally efficient, preferably of low polynomial complexity. Last but not least, following the approach is successfully applied to model checking, the so-called symbolic search approach makes the search memory efficient by storing all states at the same distance layer together using decision diagrams. Heuristics and symbolic search are currently the two dominating approaches in classical planning. Okay, so let's dive in a bit. And if you have questions so far, please ask them now. Okay, now let's dive in a bit. Okay, so the heuristic search planning was so central to the development of planning in the last 25 years. The idea behind heuristic search planning is that search guidance can automatically be extracted from the strips of SAS class representation of the planning task. The search guidance, often referred to as heuristic, is an approximation of the optimal cost of solving the planning problem, and is often achieved as the cost of solving some relaxed or simplified version of that problem. The simplest such relaxation can be obtained by dropping the delete effects of the actions. Then the cost of optimally solving the so-called delete-free task is an approximation of the cost of optimally solving the original task. Is there a question? No. Delete-free planning is simpler than strips planning, with optimal delete-free plan generation being NP-complete as opposed to p-space complete, and non-optimal delete-free plan generation being polynomial as opposed to p-space complete. Many state-of-the-art non-optimal planners still rely on partial delete relaxations or ideas derived from it. I will not go into details of the various methods for approximated cost estimates developed over the last 25 years, but will show an overview of the 5 families of heuristics. This overview is by no means complete, as this is a really active research field. Heuristics can be divided into admissible, meaning given a guarantee of never over approximating the true optimal plan cost, and non-admissible, which do not provide such a guarantee. Admissible heuristics can be used for optimal planning, while non-admissible cannot. In the next slides, admissible heuristics are marked in blue. I would like to emphasize that the computational efficiency of these cost estimates is crucial to the success of heuristic search. As I said before, these estimates should be not just tractable, but preferably of relatively low polynomial complexity. Okay, the first family is delete relaxations, with H plus being the optimal cost of solving the delete relax problem. This is an admissible and often very informative but costly to compute estimate. And therefore, it is impractical for classical planning. H max and H add are estimates of achieving the most expensive fact and the sum of facts achievement costs, respectively. HFF is probably the most famous heuristic, finding some delete-free plan. HP max is a cost-sharing approximation of H plus, and HSA is a set additive modification of HM. The last two, semi-relax and red-black planning heuristics, have gained a lot of attention in the last decade. These heuristics are based on the idea that we can relax only some of the delete effects and still get a tractable problem. The second family is so-called critical path heuristics, generalizing H max to account for the most expensive tuple of facts instead of a single fact. These are also admissible, but expensive to compute, exponential in M, the size of the tuple, and do not pay off in practice for M greater than 2.
Michael, could you repeat the HP max? I missed that.
HP max, right? So HP max is a cost-sharing approximation of H plus. It's done by Vitaly Mirkis and Herman Domschmuck. You can look up. I think it's ICAPS 2007.
Okay.
Okay, so let's move to the third family. This is abstraction heuristics, with the main idea being to implicitly define or explicitly construct a so-called abstract transition system, with the guarantee that the cost of the goal path in the abstract transition system can only decrease. Here, multiple ideas focus on ways to construct explicit abstractions or define implicit ones, ensuring that the guarantee holds. Here as well, these abstract cost estimates should be efficiently computable. And in most cases, at least for explicit abstractions, this actually holds because these heuristics are often pre-computed, and then during the search, the only computation is a lookup of value, and that is very fast. Next, landmarks are logical formula that must be true at some point along any plan. Some landmarks can be efficiently pre-computed, and the information about their achievement status can be used as a heuristic estimate. Other methods, like the famous LMCAT, computes landmarks on the fly. Last but not least, potential heuristics define some state features and compute weights for these features. An estimate of a state is then the sum of weights over the features that hold in that state. With the right features, this estimate can be both informative and fast to compute. In addition to heuristic estimates, search pruning techniques can significantly speed up the search. Similarly to heuristics, these techniques are also automatically derived from the planning task descriptions, either in strips or SAS class. The first one, partial order reduction, comes to compensate for the need to explore different orders of a planned actions, even if these actions don't have any dependence between them, and they can be executed in parallel. Structural symmetries try to capture the structural similarity within the planning task, such as similar objects, map symmetry, etc. Novelty tries to reduce the accidental complexity of the planning task, defining a series of simplified searches. Each of these techniques can lead to exponential reduction of the search space. While partial order reduction and structural symmetries are mostly used for cost-optimal planning, novelty pruning was successfully used in satisficing planning and agile planning.
May I?
Yes, of course.
Thank you for the presentation. I have a question on these methods. Are those methods problem specific? So I have to define this heuristic based on the specific problem or class of problems?
No, these methods are defined based on the. Let me show that again. I hope that I don't need to go too far back. On this, for instance, right? So this is a language called SAS+, and on this language, on problem defined in that language, I can automatically derive these heuristics or these search pruning techniques. So if you have your own problem that you want to solve, you model it in that language, you describe it in that language, and that's it. The planners do the rest.
Thank you.
So let me hope that I can come back exactly to the same place. Yeah, okay. So I hope that by now I have given you some idea about the amount of various methods for solving planning tasks. Each of these, as well as various combinations, have been implemented as domain-independent planners. Domain independence here means that there are these planners are agnostic to the source of the actual problem at hand and can solve any planning problem described in the planning language, as I just mentioned. To be able to perform an independent comparison of these planners and to facilitate the development of planning systems, a planning competition was established. The first international planning competition, or IPC for short, was established in 1998 and was run as a biannual event since then. Well, almost biannual, as you can see. The most recent IPC happened in 2018, and the next one should have been happening this year. But as of today, to the best of my knowledge, no one has stepped up to organize it. So the possibly 2022 might change to possibly 2023. One of the major outcomes of the IPC, and that outcome greatly benefited the planning community, was the development of a unified planning language, PDDL, to be used as an input to all planners. You will see examples of PDDL in the next part of the tutorial. The competitions feature multiple tracks for domain-independent planning, deterministic planning task, deterministic planning track, non-deterministic or probabilistic planning, and temporal planning. In a learning track, domain-dependent solutions can be developed based on smaller instances of the same domain. Two recent tracks are unsolvability, where a task should be proved as unsolvable, and HTN planning track, where a richer hierarchical description of the planning task can be given. Many tracks have multiple subtracks. For example, deterministic track has cost-optimal, cost-bounded, satisficing, and agile subtracks, each with its own evaluation criteria. Planners that compete in the same subtrack solve the same computational problem and therefore can be compared to each other. The rules of the competition are very simple. You submit a planner that should be able to consume PDDL as an input and to output a plan. Once submissions are closed, the organizers choose a set of PDDL domains and instances and run all the submitted planners. So the competitors do not know in advance what problems they will be solving and need to support any problem describable in PDDL. As you will see next, the range of these problems is quite large, varying from transportation to genome edit distance computation to cyber attack planning. The winners, according to the pre-specified criteria, are usually announced during the award ceremony of that year's ICAPS conference. The competitions were an enormous drive for research and planning for the last 20+ years. Many ideas were developed and first exposed at the PC. Also, the competition forces people to invest into efficient implementation and make their code usable by others. Some of the top performance of the past competitions are listed here. For cost-optimal planning, these include fast downward stone soup of FDSS, Simba star or symbolic bidirectional A star search, or Delphi, which is a portfolio planner. For satisficing, this includes a well-known planner called Llama, a portfolio planner IBACOP, planners Mercury, fast downward stone soup, and Luck family planner that performs best first with search using a novelty pruning. For probabilistic, there is a family of Prost planners, Prost-based planners. There is a random Bennett ones that excelled in different years. And for temporal, there are multiple planners that work well over the years. And there are planners that did not compete that work well as well. Yes, do we still have a question, or is it raised hand from before? No, okay.
Yeah, actually, I have a question, but I don't know if it's a good time.
It's a great time. Anytime is a great time to ask a question.
Thank you. So thank you for the overview. I have a fundamental question. How is the relationship with integer linear programming? So is it possible to cast those problems as integer linear programming?
Yes. So the simple question is, once you bound the plan length, you can cast it. You can cast classical planning problem as an integer linear problem. In practice, it does not work that well. At least it's not competitive with the heuristic search. One of the reasons for that is that the integer linear program that you create is going to be very big, because you actually need to make kind of copies for every time step, right? So your model will be quite large. At some point, your model will be too large to fit into any existing, well, not any existing memory, but any typical memory that you would have in your machine.
Sorry, another question is, what is the relationship with the technique that I use typically in the this problem, no? Like branch and bound or cutting plane, or yeah.
Right. So the search techniques that are used for integer linear program are not the best fit for classical planning, because in classical planning you actually have a guided search, right? So you have a directed or goal-directed search, right? In branch and bound is too general here, right? So the heuristic search is performed better because you go towards a goal.
Okay, because you have an initial state at
yes, you have a goal state, right? So you have an initial state, you have a goal description. It might be multiple goal states, but at least you have more information than you have. Well, it's not strictly more information, but it's a specific information that helps you search better. Okay, so while there are hundreds of planners out there, most of these planners are implemented on top of one of the following planning systems, some of which are still being actively developed. The first one is the famous FF by Jörg Hoffmann and Bernard Nebel. Originally developed as a satisficing planner, it served as a basis for many planners, including numeric, conformant, and contingent planners. Fast downward planning framework by Malte Helmert is probably the most well-known one. It is being developed by a large group of researchers and serves as a basis for most of the state-of-the-art classical planners. If you look at the planners that participated in the last APC, you will see that almost every planner there is based on fast downward. Also, many planners for richer formalisms are based on fast downward. Another planning framework is LAPSC by Miguel Ramirez and others. LPG by Alfonso Gerevini and others is performing a search in the plan space. It also serves as a basis for planners for richer formalisms, such as numeric, temporal, and diverse, to name just a few. There are other planners and frameworks like SHOP2 for HTN planning, Optic for temporal planning, and many more. Going beyond IPC planners, there are major efforts in the planning community to make the existing tools easy to use and available to everyone. Some of these efforts include the development of a planning service that captures planners for the most popular formalisms and computational problems. And this was done by our group. The service is available as a source code and as a Docker image, easily deployable either locally or on the cloud. Other major efforts are planning domains, including the restricted version of a deployed planning service for agile planning. And this service is restricted to 10 seconds computational time. And that can allow you to play around with a simple planning task. Another effort coming out of our group is a suite of planners that find a set of plans rather than a single plan. These include top K and top quality planners, as well as diverse planners. We have open sourced the Forbit iterative collection of planners, as well as K-star based ones. There is also a symbolic search based top K planner by David Speck. Other useful planners include oversubscription planners, font planners, which font stands for fully observable non-deterministic, as well as lightweight Python-based classical planner developed for educational purposes called PiperPlan. I would also like to mention the community Slack workspace, where you can get help with any issues from planning researchers of all levels of seniority. ICAP's website is also a good source of information. We have a community GitHub with some of the project developed jointly by many community members. One project that deserves a separate mention is PlanUtils. This is another effort of making planning tools easily accessible. PlanUtils provides singularity-based runnable images and running instructions for a large variety of planners, currently counting over 20 planners and tools. Last, there is also a planning wiki. While being an initial effort, it also provides a good amount of information. I just want to mention that the links to tools and planners mentioned in this presentation can be found at our tutorial webpage. It should be, the link should be in the chat, and you can also get there by following the QR code. Okay, thank you. Any more questions?
I actually have.
Of course. We have enough time.
Okay, thank you. Yeah, so I'd like to understand, you mentioned reinforcement learning. So reinforcement learning is based on the Markov decision process. So what is the relationship of I don't know, PDDL or planner? So how they typically Markov decision process, they have a probabilistic transition, probabilistic state.
Right. So let me go all the way back to.
So the simple question would be, what is the difference between SAS plus, which then it's the reference, and
so let's look at this one, right? So in classical planning model, you have a deterministic transition function, but in probabilistic planning, for instance, you have a probabilistic transition function, which allows you to basically define this as an MDP. Right, so this is an MDP. So the model for probabilistic planning would be an MDP, but in languages you have in PDDL, for instance, which I mentioned previously, you can have for these operators here non-deterministic outcomes or probabilistic outcomes. Right, you can have a deterministic precondition that will tell you whether this operator is applicable or not, but you can have a set of probabilistic outcomes. So you can have add and delete effects with probability X, or P, P1, add and delete effects with probability P2, or add and delete effects with probability P3, and so on.
So this does it mean that the NDP can be described as a SIS or a strip, or the other way around?
Yes, exactly. You can use well, it's not a strips language; it's a different language. But you can use a PDDL, probabilistic PDDL, for concisely defining a large NDP.
Sorry, it's not clear. So MDP will be a subset of this planning tool, or
yes?
Okay. So
MDP is one of the planning models, yes, for probabilistic planning.
Okay. So this planning will be more flexible in the sense that this transition can be of various type, whereas an NDP is typically only probabilistic. There is no condition apart from the state and the action.
Well, there is a condition, right? Because some actions can be just self loops, right? Because they're not applicable in that state. Right. So if you look at an MDP and you look on the transitions that are not self loops, right? These transitions correspond to applicable actions. So applicability is defined by the precondition in planning. So
Okay.
let's look at this, right? So you have a set of actions A, S that are applicable in state S. And these are a subset of all actions.
Yep.
Right? And this applicability is defined in the planning language by the preconditions. So an action is applicable, let's go here, right? So an action is applicable if the precondition is included in the state.
Yep.
Right?
So
in,
what is
in richer languages, for instance, you will have a different transition system, right? So the transition will be probabilistic, defined on what you use in PDL is one-off, for instance, right? So you have a one-off possible outcomes, each with its own probability. Unfortunately, I cannot open now a PDL example, but you can easily find it, right? So if you look for PDL for things like I don't know, briefcase world, something like that.
So these SIS and strips allows for richer description. So for the model
SAS plus and strips are classical planning languages, and in classical planning you have only deterministic action outcomes. But in other languages allow you for non-deterministic outcomes or probabilistic outcomes.
Thank you.
Yes.
I have a high level question. So when I first encountered AI planning community in the 1980s, it was very distinct from the heuristic search community. And the heuristic search community, they didn't talk to each other, right? And the planning community was all about logic and correctness. And of course they were doing search, but they didn't emphasize search, right? And they certainly didn't emphasize heuristics. And the planning community, the heuristic search community was all about vector representations and things like that. And my impression is about 20, 25 years ago, that changed around the time of fast forward. And that now, at least the planning community certainly borrows ideas from the heuristic search community. For example, Monte Carlo tree search would be commonly adopted by, it would not be crazy for a planning person to use MTCS. Has the opposite happened? Has the heuristic search community adopted ideas from the planning community, or are they still separate and a ghetto?
I think so, yeah. So at least I am aware of a few instances. Some of it maybe.
Do they use richer representations in particular?
Oh, that I actually don't know. But I have seen some instances of borrowing ideas, like the idea of cost partitioning as a means to admissibly join multiple heuristic estimates. So search pruning techniques definitely were borrowed back.
Okay, and one more question. So does means ends analysis still have a bad reputation in the planning community?
I don't think so, no.
Well, so certainly in the days of the partial order planners, if you mentioned that you were interested in means ends analysis, they would just laugh at you because of the Sussman anomaly. And I think there have been plenty of demonstrations since then that it's not that big a deal, but certainly the whole shift to forward chaining, which of course is partly what made the gap between planning and heuristic search, why that reduced is the shift to forward methods. That has reduced the concern about means ends analysis, but means ends analysis is arguably still using some backward chaining ideas in it. So anyway, I grant you that this is not part of the mainstream, but I'm just curious because I'm interested. Of course, I would think the first planning system was GPS, the general problem solver.
Yep.
And it doesn't usually get much acknowledgement as that. It usually strips, which used this, or pretty much the same algorithm, is viewed as the first planner, and yet somehow both of them. But and I'm interested in how people do planning and incorporating ideas from how people do planning into AI systems. And I just was curious if that's getting any attention now. My guess is not so much.
Yeah, not a great deal of attention. I agree. Yeah, but I mean, okay. So backward chaining is actually somewhat regained popularity in symbolic search, for instance, right? When you can actually, well, maybe backward search rather than backward chaining. Because there you can actually compactly represent this, right? There is no issues of spurious states or unreachable and then that, right? So, but in principle, I would really like to see the comeback of many ideas. And reading all papers, I really look at this and see how is that forgotten, right? How is that not used right now in many cases, right? And yeah, I completely agree with you.
Okay, good. I have other questions, but I'll wait if other people have things to say.
May I follow up on this discussion? So do you think those methods that you listed could be applied, as mentioned by Langley, to, for example, Monte Carlo tree search, in order to speed up the search or reduce the search space?
Which methods?
I don't know. You listed quite a few.
Like heuristics. I mean, Monte Carlo tree search is a heuristic search.
Sure.
Right? So,
but it's probably used a simple version. No? I suppose it's just.
Yeah. So there are a few works that actually use Monte Carlo search for classical planning. Don't forget that you actually need the classical planning model in order to derive those heuristics, right? It's rarely the case that you have the classical planning models in applications that are currently using Monte Carlo tree search. It's not. It doesn't mean that there are no way of deriving that planning model. Just that people don't do that. But in principle, and also, I mean, if it's like, it should be like a single search, a single agent search, right? Not like in AlphaGo when you have multiple agents, right? Multiple players. But yeah, it's definitely possible. People are doing that. People are using Monte Carlo tree search with classical planning heuristics. With search pruning techniques, it's probably not the case, because it doesn't really make sense that Monte Carlo tree search is a greedy algorithm anyway. So.
Thank you.
I got one. Maybe I don't know what I got here late, so I don't know what the schedule is for the tutorial. Are you going to talk about learning later?
Not that much, no.
Well, then let me ask a quick question. In classic work on learning and planning, there were two main approaches. One was to learn symbolic conditions under which you might want to apply an operator or select a goal. And this doesn't. Now, I'm not just talking about systems like Prodigy. I'm talking about even farther back with some of the pre-Prodigy forward chaining problem solvers. And the other is to learn macro operators, right? So one reduces the effective branching factor, the other reduces the effective depth. But of course, in the heuristic search community, a more classic way to do learning would be to try and learn an evaluation function. And that maps more directly onto what reinforcement learning does. If you think about it, that's really what reinforcement learning systems are doing, is learning evaluation functions to guide search. And of course, they're not antithetical. You could learn search control rules that had some kind of, that you could combine them. But what is the state of work on? Oh, and then there's, related to learning macro operators, is work on learning hierarchical task networks, which could be viewed as a very flexible kind of macro operator. So what is the state of the field on learning and planning? And in particular, is there anything going on besides applications of reinforced learning?
Oh, okay. So, yeah, thank you for that question. It gives me the opportunity of promoting our workshop on planning and reinforcement learning that will happen at ICAPS this year, and happen for running for a few years now. This is the third year for that workshop, and focuses on these problems exactly. There has been a regained interest into learning distance estimates and in learning errors in distance estimates as well, which is kind of more it seems more promising to me, at least, and not just because I was one of the co-authors on that work, because of the domain of the values that you actually can get for a heuristic function when you move from smaller problems to larger problems, right? So there is an issue of your when you learn the heuristic values, you don't observe large heuristic values on small problems when you actually have the data. When you move to larger instances, then you have an issue, right? So we just had a paper accepted to this year's ICAPS on that with Leslie Camblin and her group. We have seen additional sources of information that people are trying to learn. For instance, given multiple possible estimates, which of these to use during search. Right? Some of the estimates can be more informative and harder to compute. Some can be quicker and less informative. Sometimes during the search, you don't really need to invest the time into computing more informative estimates. Sometimes you want to actually do that, right? Depends on where in the search you are. There has been a lot of work for the last, I think, 2 decades on learning the planning models, whether it's classical planning or HTNs. It mostly focused on learning models from traces, but I think there were additional work that kind of tried to learn models from scratch. There is a lot of work on when you know the structure of the model, just learning the planning instances, and that's very related to what Shirin is going to talk about.
When you say learning the models, are you talking about learning action models? Or are you talking about learning heuristics?
So when I talk about learning models, I talk about learning action models, yes. But there might be also that you know the lifted action models, but you don't know the actual instances, right? So you don't know the objects, you don't know the static predicates that will tell you which are the grounded actions actually relevant to this task, right? And so there was so the focus was mostly on these topics, right? But there was also a focus on solving the reinforcement learning task, right? So, with Python.
Well, my question is whether there is any work still in the old paradigms of learning symbolic control rules, as in Prodigy, or learning
Mm-hmm.
macro operators, because in the 80s and 90s, that was most of what was going on. And then reinforcement learning came along, and it was very alluring to many people. And yet maps more directly onto learning numeric evaluation functions. But of course, the word heuristic always had this dichotomous meaning. Some people meant a numeric evaluation function, others meant, quote, rules of thumb. And so, you know, there was a 10-year or more effort in the Prodigy community that was getting some really impressive results that seem to have been lost to the community. I'm just wondering if any of those ideas are still alive and well.
Yeah, so there was work in 2004, I think, by Adi Bota and others on learning macro operators. There was a few follow-up work by Derek Long and Maria Fox from London, King's KCL, right? And by Cole's couple from KCL as well. I think it was actually before they joined KCL, so but around those years, right? The most recent that I can think of is only the one that I was involved with, Ishkai, last year, and that wasn't actually on learning planning macros for planning operators, but just for black box planning. And so, like, basically search. And so it focused on learning useful sequences of action applications without action models, actually. But that work is actually currently extended into deriving action models for macro operators. So yeah, there is a little bit of work, but not as much as I would want to see.
Okay, good, thanks. I'll send you a link to some really early work on learning evaluation functions by Larry Rendell that you might find interesting.
I would love.
But basically, this was in the heuristic search forward chaining kind of framework. But he was learning numeric evaluation functions, basically stated as regression trees. It's almost unknown, and I think you'll find it interesting. It's back in the 1980s. Okay, thank you. I'll let you go.
Thank you. Yeah, would love that. Thanks. Any other questions? Okay, then according to our schedule, we have now a 40 minutes break. 40 minutes break, and we will be back at 1:30 for the next part of the tutorial. 1:30 according to EST. Right? So I'm sorry. It's so in 40 minutes from now, we will start the next part of our tutorial. Thank you. See you back soon.
All right. This section is on modeling, and we'll go right now. It's 1:30 p.m. Eastern time, and this will probably be roughly about 35 to 40 minutes, maybe shorter. Then we go on another break, and then we go on the practice section that will be run by Octavian Rudra. All right, so as I said, we consider any gap between identifying that you have a planning problem at hand, that you can use a planner to compute its solution, and specifying a planning problem in the language such as PDDL or planning domain definition language, in order to use a planner to compute a solution to the original problem to be a modeling challenge. Now, this requires obtaining the knowledge, representing the knowledge, extracting it, possibly learning it, validating, as well as updating and enhancing the knowledge. So some modeling challenges are you often need to transform the original problem to a problem with a known or easier to compute solutions. Now, this is in the same line of work as this transformation compilation steps that are often done to solve a hard problem using a relatively easier and with known solution problem. Two, access to domain experts familiar with input to planners, such as PDDL, is very rare. Also, any form of knowledge is practically guaranteed to be incomplete and often inconsistent. Even human validation can be ambiguous. Now, current state-of-the-art learning approaches may not scale and may have assumptions that may not hold for practical setting. Furthermore, the learned knowledge may not be consumable. Now, let's drill down more on this first challenge on establishing the relationship to AI planning. Now, sometimes it's trivial to write down a planning model. Sometimes it's not. You need to find a relationship to an existing problem with established connection to AI planning problem. We call this a planning problem in disguise. Then you need to define the original problem and make the correspondence to AI planning. You need to reduce it to a problem in which an established relationship to AI planning exists. This allows us to use AI planning tools to compute a solution, and then you can post-process the results to compute solution to the original problem. Now, in the case of scenario planning problem, which was an example I introduced in the intro, you first have to define a scenario planning problem, then make a correspondence between the scenario planning problem and the plan recognition problem. Plan recognition is the problem of recognizing plans or goals of one or more agents with a series of observations given to you. So that is, we link the relationship between the different forces such as technology, currency, social order, corruption, natural disaster to an AI planning task. The drivers that users select for their what-if analysis become the observations. The implications, the drivers that have special importance to the users, are then the goals. Then we need to leverage this existing relationship between AI planning and plan recognition in order to compute the solution to the original problem. Now note that sometimes you do need to extend the existing relationships in a number of different directions. So for plan recognition as planning, we had to extend it to consider observations that are over fluence or properties of states, and that they can be unreliable. So not all observations are explainable. Now, I want to point out that there are several established relationships to AI planning that's often explored. Some examples are listed here. So for example, finding excuses, diagnosis as planning, explanation generation as planning, as well as plan recognition. This in turn helps with other problems such as hypothesis generation and exploration, future state projection, multi-agent plan recognition, as well as scenario planning. Now, in addition, I want to mention that there are some other commonly used compilation techniques that can be used when it comes to the modeling challenge. Two examples are as follows. You can compile away soft goals. This is work by Kaider and Geffner in 2009. This will allow you to use any classical planner to obtain a solution for a planning problem with soft goals or simple preferences. Another technique is translating the HTN problem into a classical planning problem. This is work by Alfred et al. In 2016. This will allow you to use a classical planner or even heuristic search to find solutions for an HTN planning problem. Now, an example application where we have used these translations from HTM planning to classical planning, as well as the compile away soft goal, is the automation of machine learning pipeline generation. This is the write down application on this slide. So the problem is that the space of possible pipelines is huge. Humans can explore only a tiny portion of it. And humans are often biased toward the pipelines that they already are familiar with. The benefit you get is generation of pipelines of high accuracy automatically, and reducing the need for human data scientists. Our solution uses planning tools for exploiting the space of possible pipelines defined within the use of regular grammars. We then translate these regular grammars to HTM planning problems and then to classical planning model. We enrich this planning model with user-defined constraints, which I'll talk more about it in the next slide. And we use AI planning to solve the planning model and translate plans to pipelines. Now, to give a full picture of all the translations going on and the use of AI planning, here's an overview of our solution to the automation of pipeline generation. Given a data science grammar, we transform it into an HTM planning model, then to classical planning model. We integrate user-defined constraints, turning the classical model to classical planning model to classical planning with soft goals. We compile these soft goals away, obtain again a classical planning model. We then use top quality and diverse planning to generate multiple plans, each post-process into machine learning pipelines. The pipelines are then trained on specific data sets, and their accuracy feedback is used to adopt a planning model. Now, in order to focus the exploration of valid pipelines, we allow for specifying preferred non-terminal as well as terminal symbols. The non-terminal symbols correspond to the rules of the grammar and allow to prefer, for instance, using a particular family of algorithms. Choosing terminal symbols allow for preferring a specific algorithm or even a specific value for a hyperparameter. The preferences are then translated to soft goals, which are added to the classical planning problem instance. Then the soft goals are compiled away using the transformation proposed by Kyler and Geffner, giving us again a classical planning instance. Now, I want to mention that the third part of the tutorial that Octavian will cover is going to go a bit more detail, actually, in great detail on this particular application. Now, let's talk about the planning language, or the representation of the domain knowledge. Here, the example I'm showing is in PDDL, or Planning Domain Definition Language. And as was mentioned by Michael, there are other languages such as HDDL, this language for hierarchical planning, or RDDL for probabilistic planning. And here we're just going to go over PDDL. Also, in the section, Michael talked about strips, the language to define the planning problem. And strips is a subset of ADL. PDL is a standard input language for planners. And originally, this was for the purpose of international planning competition that runs every 2 years since 1998, I believe. You can define both types of problem strips as well as ADL in PDDL. Now, in PDDL, you define two files, the domain file and the problem file. The domain file includes a description of actions, list of predicates, and types, if any. The problem file includes the initial state, goal state, and the objects. So here's an example of a Myconic elevator domain. The domain file has actions for boarding a passenger at a particular floor, departing a passenger, as well as the elevator going up and down. The initial state includes information about the passenger, locations, floor numbers, the original and destination location of the passenger, original floor of an elevator, as well as predicates to define the relationship between floors. The goal is to serve the passengers, and they're defined in the problem file. Now, normally the domain file is fixed, while the problem file can vary. And here there are 4 passengers and 7 floors. Normally, you have a generator that generates many different sizes of the same domain. And finally, when you run the planner, you see a plan that would be the sequence of actions on the right. And this is automatically generated for you. Any questions? I see some on the chat, but I can't see them yet. Anybody wants to raise a question at this point? Yeah, feel free to do so. Okay, I want to point out that there are many examples of modeling tools that has been developed. And here I'm showing some of them that were developed at IBM. There are many others, of course. The tools are developed because oftentimes you want to interact with the domain experts. They're not familiar with PDDL, but would like to obtain the domain knowledge somehow. And I like to point out that these languages and modeling tools are just proxies for obtaining the domain knowledge. Once the information is obtained from experts, it's automatically translated into PDDL, which would be the input to the planners. Next, I'll go over some of these modeling tools. Now, first, I want to drill down more on the hypothesis generation problem, which is the left top example on this slide. So in this example, we are in the healthcare setting, actually ICU setting, where a patient is connected to several monitoring devices that measure their physiological states. And these are attributes such as a patient's blood pressure, heart rate, and temperature. The analysis of these raw streams of data results in semantically meaningful observations about the patient. For example, given the patient's heart rate, their respiration rate, and their body temperature, which are measured continuously, also their white blood cell counts, you can obtain something that's called systematic inflammatory response syndrome, or in short, SIRS, which will give you a number between 0 and 4. And this score is a meaningful observation about the patient's health. Observations can also include other measurements that are provided by physicians or nurses, such as their assessment of patient's health or a result of a lab. Note that these observations are partially observable and also noisy in nature. So a simple model that represents transitions in the healthcare application is shown here. Nodes are states, and observations are the ones that are connected to these states, and those are the ones we saw in the previous chart. So the patient is initially in a state called start, then they're admitted, then they can be in either a low risk or high risk state, and things can progress to pre-complications and other states. Note some of them appear in, some of these observations appear in more than one state, and those are called ambiguous observations. And now our goal is to generate hypotheses based on the model and the observations that we're given. As I said, the observations can be unreliable, they can be noisy, they can be missing or incomplete. So therefore, some observations may be left unexplained by the hypothesis. Now, in order to capture this domain knowledge, we propose a language that's called LTS++. This is based on labeled transition system, or LTS, and we build an integrated development environment around it. Using a screenshot of this tool, the LTS+ representation of the same model that we saw in the previous chart is shown here. I won't go into any details here, but basically you can see states, class types, and the connections to observations. Now, everything we described in LTS++ is then automatically translated in a PDDL. To do that, we have defined a fixed planning domain that's shown here. and then varied the planning instance based on the given LTS++ model. So this planning domain contains 6 actions: explain observation, discard observation, state change, entering a state that's good or bad, and allowing a state to be unobserved. These are very generic actions that we define. Then based on the input that's written in LTS++, we generate these problem instances automatically. So here's an example of an output of a planner, the screenshot of the actual tool that we have developed. The input is shown in green, and that's the OHH1, OSIRS0, and SIRS2. This is the sequence of observations that we want to generate a hypothesis about. The state transition system is, as we, it's a subset of it is shown here, but is the big one that we have seen in the previous charts. And we have seen the PDDL problem and domain file or example of it also previously. Then we are ready to run our planner of choice. And in this case, we run a top K planner, computing top 4 plans as shown here. So these are the plans 1, 2, 3, 4 in each row. After post-processing, we can visualize these plans and show them here as hypotheses. Now, each hypothesis is shown as a sequence of states that are matched to observations. Now, the first 3 hypotheses explain all of our observations, and the last one doesn't explain the first observation as shown in purple. Now, a lot more can be said on this application and LTS++. I would just say that while I showed this example in the healthcare setting, we worked on a number of different other applications within this framework. And in particular, Octavian will talk about the malware detection application in the tools section. All right, I'll pause here to see if there are any questions.
Sharon, I'm having trouble understanding if this is a plan recognition task, who is the agent?
In this example on the healthcare setting, we didn't really connect it formally to plan recognition, but you can think about the user being the nurses or doctors trying to figure out what's going on with the patient. So it's for them.
I think it's fine. I just don't. If it's neither plan generation or plan recognition, then this is a great, interesting problem, and I see that you can use a PDL notation to describe what's going on, but it seems misplaced to me here. Am I confused? Am I in the wrong tutorial?
No. So while we didn't really make the at that point, this was in work in 2011. We had just published 2 pieces of work on diagnosis as planning and also explanation generation as planning. So we made the connection to those, and that was sufficient. But as I'll talk more about plan recognition in the work on scenario SPA or scenario planning, then we actually made the formal connection to plan recognition. So it's basically, I think, is mostly the time frame of how all of these pieces, pieces of work have actually came out. But you're absolutely right. There is a relationship to plan recognition here as well that was not fully explored at the time.
Well, I guess you could view God as being the agent or something, but maybe he didn't. Whatever. I mean, the thing is, in plan recognition and in plan generation, there's choice, right? And this is a natural system that if it's not deterministic, it's only because we don't understand it very well, right? I mean, we believe that whatever happens in a medical scenario, it is determined by the situation. So it's not a plan generation task. I would say that could easily be viewed as some kind of explanation or as a monitoring problem. So again, I'm excited that you found a way to use a planning representation for this. I'm just wary of calling this a planning task. That's all. But I guess you can always you can view anything as anything else if you want to. So please go ahead.
Right. Yeah. So as I said, a lot of these applications are not your typical, initial state goal planning applications. It's about finding connections to some other existing work. And in this case, it was actually explanation generation as planning. Yeah, you're absolutely right. Point well taken. Any other questions?
Shireen, just a quick question. Is LTS++ publicly available, or what is the, in this line of work, what is the most stable tool that is available? I'm just kind of curious.
Sure. So LTS++ is not available, but of course there are papers, and we have actually recent journal paper that explains it in detail. Scenario Planning Advisor, which I'll talk next, is available as an open service for non-commercial purposes, and you're welcome to use it. The other very recent work, which I'll talk about in the end, is the work that's recently going on as Dialogue as Planning, and there are two recent products that's coming up, Watson Orchestrate and GOFA. So I'll talk just a little bit about that also in the end. So those are, I would say, most recent in terms of the timeline speaking. Okay, great questions. All right, so next I'll talk about scenario planning application in a little bit more detail. With respect to here, the focus is domain knowledge and obtaining this domain knowledge. So scenario planning is about identifying and managing emerging risks. It's a commonly used method that various organizations use to develop their long-term plans. Scenario planning involves analyzing the relationship between forces such as social, technical, economical, environmental, political, in order to explain the current situation, in addition to providing insights about the future. Now, one of the main tasks, in addition to the automation, is gathering this domain knowledge from experts. Our first attempt was to use mind maps to capture this knowledge. So rather than specifying the domain knowledge in PDDL or planning terms, which are hard to do, we created a way for domain experts to specify the domain knowledge in mind maps, and then automatically translated these mind maps into PDDL. Here's an example, or two examples of mind maps. These are two mind maps that are connected by a common node. That's the decrease in price of commodity that's in both of these mind maps. You have the central node, which is here currency depreciation against US dollar. You have nodes on the left and the nodes on the right. The nodes on the left are the causes, and the nodes on the right are the consequences. So the way to read this, for example, is that high inflation may lead to currency depreciation against US dollar, which may lead to increase in taxes. Now, we allow for customizations of these mind maps as well. And the way we've done it is through a questionnaire. So for example, here users can answer the question of how likely are any of the following to lead to currency depreciation against US dollar. And this will allow customization of the mind maps. Now, so we started with mind maps as a way to capture the domain knowledge. We worked with domain experts that provided this knowledge. And during this process, we realized that for a reasonably sized set of risk drivers, domain experts can take days to weeks to express their causal knowledge. Now, writing the knowledge in mind maps helps to some extent, but it is really impractical, especially with regard to maintaining that knowledge. So on the other hand, causal knowledge can be extracted from experts' authoritative documents using natural language understanding, or NLU, orders of magnitude faster. So the best solution we have so far is we use learning-based natural language understanding techniques to identify risk drivers and extract causal pairs. We use AI question answering for automated reading comprehension. We ask the questions of what causes X, and this requires no supervision. This is best done using documents that are rich in content, especially causal content. For example, 10K reports and NATO SFA reports. We ask open-ended questions based on seeds and risk drivers, and this will allow us to discover new candidates, and it also helps with bootstrapping. Now, for causal extraction in support of planning model generation, we had a few options. For SPA, we created a tool called CFAS, which is causal extraction from authoritative sources. As I said, it uses AI question answering to answer causal questions about risk drivers. It relies on relatively small set of documents, for example, here US Secretary and Exchange Commission's form, or 10K, each of which is a comprehensive reports filled annually by public companies about their financial performance. And specifically, item 1A, risk factors, provide detailed coverage of company and industry financial risks. Now, for NATO strategic foresight analysis document, a periodic analysis of global risk in all areas of risk, including, for example, social, political, environmental, and economical risks as well. Now, CFAS processes all of these input documents, asking for each paragraph of each document, and for each known risk driver, questions such as what causes D and what does D cause. Now, I like to drill down on another application, which is planning for dialogue, and I'll go over it very quickly. So what is the current state of conversational agents today? Well, the market size is big. There's lots of money, and there is a lot of focus directed toward dialogue agents. The potential saving is also substantial. And we know the current players. We know, for example, Google, IBM, Apple, Amazon, and Microsoft. Each of them have their own tools, such as, for example, Siri or Alexa. And we also know that there are many deployed agents that have really undesirable behaviors. So, for example, on the left is the state-of-the-art in a livable agent that's using machine learning or deep learning. And this is an image of, for example, RNN approach. So the agent says, hello, how can I help you? And the user says, I like a trip to Toronto, please. And the agent says, okay, a trip where to? The user says, never mind. Now, next example is an imaginary great DL approach. The agent says, hi, what seems to be an issue? The user says, all of my emails are gone, help. The agent says, I understand entirely how frustrating this can be. We know exactly what happened and we have it resolved in an hour. If you like to check the status, the ticket number is 123. And the user says, well, that's a relief, thanks. So the point is that the provided information here, in particular the ticket number, can be useless if it's not connected to an API. So the ticket number is either a data leakage, for example, or could be potentially fabricated. So in terms of dialogue as planning, the setting is a multi-turn, goal-oriented dialogue. And the challenge is how to scale beyond explicit trees. Now, the solution is to not define the dialogue tree, which can be very large and hard to maintain. But that's often the case that's currently done in current systems. but to define the mechanism for the domain declaratively via planning, and then let the planner generate the tree automatically. Now, model acquisition, model learning, refinement, they're all important problems in this application. Now, a key difference to the imperative design approach, somebody manually defining a dialogue tree, and that is, instead of starting with the users and that says, figure out different ways of how to react based on this dialogue tree, it becomes, these are the bot's capabilities, these are the different skills and so on. And here are the goals that you need to achieve. So concretely, the bot is on the nodes and the user's environment are the edges or the outcomes. Now, I want to point out that this approach also addresses the tri-state variables, so that things that are known can potentially be modeled here as well. And also stateful conversation patterns such as slot filling or confirming things or digression can also be modeled as simple planning constraints as well. So the tool is called D3WA. Here are just some screenshots of the tool. With this tool, you get exponential scale up, increased sophistication of dialogue tree with same size of a specification, and decreased size of a specification for same sophistication of dialogue tree. The modeling space in D3WA does allow you to have debugging guidance for the domain author, and also allows explainability for the user as well. Now, two other recent and related tools are IBM Watson Orchestrate and IBM App Connect. These tools combine the power of natural language processing and AI planning to address the conversational agent problems. So here, you have conversational agents that are realized as an aggregation of skills. And at runtime, planners can be used to organize assets dynamically to fulfill user goals extracted from natural language utterance. There is ICAPS demo as well as AAAI demo link here. And there is also a BPM tutorial that the link is here. It does include functional PDDL models that you can play around for D3WA, as well as Watson Orchestrate. Now, there are lots of other approaches and systems that we didn't cover today. Here are some examples of those. There is It's Simple, there is the PDDL editor, there's PDDL in Python. This is very recent and very interesting line of work. There's also Plan Animation, and there's also PDDL plugin for VS Code as well. There's also an active workshop at ICAPS on knowledge engineering for planning and scheduling, or CAPS, that happens every year at ICAPS. There is also a book on PDDL entitled An Introduction to Planning Domain Definition Language that was published recently. There's also extensive literature on planning and learning, which we did not cover. This addresses the learning of the planning actions from some input traces. They're using variety of different techniques such as MaxSat, Markov logic networks, graphical model estimation, generic algorithms, and finite state machines. So modeling is an important aspect of use and adaptation of AI planning. As we saw, investing in this transformation and compilation techniques pays off. And as we saw, several applications use these compilation transformation techniques. Also, learning consumable planning, or even some subset of it is important, when enhancing a planning model automatically is important, as we saw in many real-world applications. All right, so this concludes the modeling section of the tutorial, and yeah, we'll open it up for questions. I'm also looking at chat. which seems to be very active. Okay, so there's a question I see by Pat on what mind maps is. So mind maps is basically a graphical, very simple way of graphically representing transitions in by itself. It has no semantics, but we were told that it's easy to use for experts, and the experts will be able to specify the knowledge in those mind maps. And as I saw, you probably saw, I show an example of mind maps, but actually expressing the domain knowledge in mind maps could potentially be time consuming and impractical. So we did go on the path of learning the whole thing altogether. All right. And I see the question on LTS++ by Biblov, and no, it's not currently available, but I can send you links to the paper. All right. Okay, so if there are no other questions, we'll be back in, let me see, I believe in 20 minutes, or hold on.
Yes, in about 20 minutes.
Yes, in 20 minutes.
I will share my screen. Yep. Then there's a QR code in there in case you want to set up and want to follow along with what I'm doing. You have the time to do it.
Yes.
Sharing, if you can stop sharing.
Yes, correct. Yeah.
We'll start sharing, and let's confirm that this is actually visible. Yep. Can you see?
Yes, we can see your screen. All sounds good.
All right. So following that QR code will lead you to our GitHub, and you'll have instructions there. Welcome back, everyone, to the AI planning tutorial. The third and last part of this is a hands-on exercise, which you can follow along with me, or you can do later. The code for this is all open source. But before I jump into it, a little bit of an introduction. My name is Octavian Udra. I'm currently a principal research scientist at Data but before this, I was at IBM Research for 12.5 years, working with Shirin, Michael, Anton Ryabov on many planners and applications of planners. I've been involved in most of the applications which Shirin described earlier in the modeling section in some capacity. And I have to say that although I'm not a planning researcher, I found planning such a useful set of tools that I've been able to masquerade as one for quite some time. But either way, today I'm going to walk you through one of those applications, the ML pipeline exploration one. Again, the code is open source. You can follow along with me, or you can follow me and try to do it afterwards. And we welcome any questions now or after this section. So do please interrupt me if you have any trouble. Okay, so I have just a couple of slides to begin with, and then we're going to jump straight into a notebook, and I'll walk you through the tutorial step by step. I think you've already gathered this from what Shirin described, but based on my experience, there are many challenges of using AI planning effectively in applications. And although it's such a useful set of tools, there is a startup cost in using this as a tool that these are worth mentioning. So in most applications, the actual application domain is not directly expressed or even expressible in some situations as a planning domain. So you're not going to get PDDLs for most of the practical applications you want to build. There are very few integrated tool chains for AI planning. So what I mean by that is end-to-end, that will take you from an application domain through kind of a transparent compilation to a planning domain, and then back out the other way to the set of results that you would expect in the application domain. And there are relatively few libraries and frameworks that integrate AI planners. Unlike the case for machine learning that has a lot of libraries and frameworks that are open to a wide set of developers, that's not always true of AI planners. And that makes round tripping a little bit cumbersome, but hopefully I'll be able to walk you today through a very simple version of an actual application which we built which shows you that that round tripping is indeed possible mostly with open source tools. So one of the main issues that you always found while building applications with planning was the pre and post processing. So getting from that application domain to the planning domain and back again from the plan results to the application domain results. And typically the types of questions I ask when I do that exercise is, how can we derive an equivalent between the desired outputs and the plans? So how can we solve a search problem for a plan, and then how can we translate that plan to a desired output? I see a question there on the chat about round tripping. That means going from the application domain to the planning domain, finding plans, and then going back into the application space as a result. So in this case, I'll give an example. We are trying to explore ML pipelines. So the application domain is that of a data science grammar. From that, we're going to derive a planning domain. From that, we're going to derive plans. From the plans, we're going to derive, we're going to create machine learning pipelines. And then if we want to make a change, then how do we kind of go around that process again in a transparent way to the developers? You're welcome. So then there's the question about our inputs, and are they close enough to a planning formalism, and then how do we map them to actual planning actions? So we'll answer those in the tutorial today. And a very important problem that always appears is kind of the maintenance actions. So typically when you do this translation, it's not going to be perfect. So you're always going to have some sort of an actions that maintain some information for you to be able to derive back the results, in this case, the machine learning pipelines. So you're going to see some of the examples of those maintenance actions today. So the question is, how do you manage them? How do you know to eliminate them from the plans in a meaningful way? But I'll walk you through that today. So what's the application space of today? Shirin already described this problem. We want to be able to explore a large space of ML pipelines, and the space is huge. So if you ever looked at, for instance, Kaggle competition, the typical pipelines that appear in Kaggle competitions, they're very often extremely involved, to the point to where they use estimators to create derived features, which are then used to train other estimators and so on, and other classifiers and so on and so forth. And the reality is a lot of this is kind of human creativity, and people are typically biased towards what worked for them before. So the problem of exploring a huge space of possibilities seems like a conceptual match for planning, although we're not quite there yet because we haven't solved the problem of goals, right? And the whole purpose of this is to reduce the need for data scientists to kind of derive one-off pipelines, and to have kind of an automated process where, given a problem, given a data set, we can explore many pipelines that are suitable for that, train them, figure out which are better, and kind of have a continuously improving process. And I'll walk you through one iteration of that loop, and then as homework, you can do it automatically for multiple iterations. So let me tell you briefly what we're going to do in the tutorial, just with a pictorial, and then we're going to go off to it. We're going to start with a data science grammar, and I'll discuss the pros and cons of that. But essentially, this models a very small subset of sklearn for the purposes of this exercise. We didn't want to model the entire space of sklearn because we would have way too many pipelines, too large of a grammar to explain really, and so on and so forth. But we took a very small subset of sklearn, and we kind of created a description of what meaningful pipelines would mean in this context. So that's what the grammar expresses. What are the rules for bringing these pieces of sklearn transformers and estimators together in a meaningful pipeline? Grammars have kind of this top-down structure where you have the the root element, and then you have kind of decompositions of that. So that's very similar to the HTN formalism for planning, where you have multiple methods of resolving a task, and then each method can be further decomposed down. So given that natural mapping, the first step is we take that grammar and we basically create an HTN planning domain from it. Then there are open source tools, not ours, but Alfred's, Kutter's, and the Now's for translating HTN to PDDL. so the standard planning domain definition language. And then once you have the PDDL, then you can solve it. You can apply a planner, and we use a top K planner to basically give us more than one pipeline. So give us the top K pipelines according to some optimization criteria, which I'll specify during the tutorial. So once the PDDL planner solves that, essentially each plan corresponds to a pipeline. And then what we can do is we can actually do training on those. So we can train we can do some hyperparameter training for those pipelines using hyperopt. And then we can measure the accuracy on a test set. And based on that accuracy, we can adjust some of the constraints, some of the costs we have in our planning problem, so that we get better pipelines next time. And we can repeat this loop that you see here on the right, however many times we would like. In this tutorial, I'm only going to do it once. And then as an exercise, you may consider, doing it automatically a number of times. We do have results on this published, but I'm going to get to those after the tutorial. So without further ado, I'm putting the QR code here again, just very, very briefly, and I'm going to stop sharing for a moment and start sharing my virtual machine. This is an opportunity for you to ask any questions. So let me stop sharing. And now I'm going to share this. So hopefully everybody can see into my virtual machine. You can see a Python, a Jupyter notebook in there. Can somebody confirm?
Yes. Sounds good.
All right, perfect. So, so here's what we're gonna do. We're gonna go through that loop number of times. Now, to give you a brief view behind the scenes, like what are the intermediate files? What do the PDDL files look like? What do the HTN files look like? I've created this directory called output. I just wanna check that it's clear. Yep, so there's nothing in it, so I cleared everything. So just gonna start from there. And the files, the temporary files that go between the cells will accumulate in there. And I'm gonna use an instance of VS Code just to get some syntax coloring of the PDDL to show you the various artifacts that get accumulated there. The main results will appear on the Jupyter notebook. And again, there are instructions on how to run this on the GitHub. So just for preliminaries, we're going to do that. We're going to recreate the output file. And actually, I think I have to exit this VS Code. Just make sure I run it from the new directory. And so I'm just running code again in the new output directory that was just created, just so I have it there. And then I'm going to hold it open there, and files will continue accumulating in there. All right. So the first thing we're going to do is we're going to take the grammar in extended BNF format, and we're just going to copy into output so we can visualize it in that same VS Code. And now I'm going to go to VS Code, and there it is. So this is kind of the BNF version of this grammar. I didn't install the VS Code extension for this, but you get the idea. So again, this is a very, very small subset of sklearn, but essentially what it says is this is kind of the start node, and it's essentially some sort of a graph followed by an estimator. And by the way, I'll get to what these strings are in a second, but remember I talked about maintenance actions. So some of the maintenance actions will have to do with these strings. What we're gonna do in this tutorial, we're gonna generate pipelines in using a library developed by IBM, but that's open source, called Lale, L-A-L-E. And that allows you in Python to essentially, it overloads some of these standard operators in Python, like this one, to allow you to essentially write pipelines in Python as an expression, right? So we're essentially going to generate expressions that Lale can that use sklearn classes, and then Lale can essentially interpret those, run them on data, they use hyperopt to train them, and so on and so forth. But the grammar that we currently have is essentially a directed acyclic graph, followed by an estimator, and the DAG itself can be pretty complicated. So it has multiple non-terminals, and it's recursive. So it's write recursive. So, you can have multiple instances of this graph kind of recursively repeating there. Typically, when you have multiple branches in this graph, they have to be followed by a concat operation. This is something special that Lala understands, where it basically takes the features derived by two separate parallel branches and it merges them together in one feature space. And this is followed by an estimator. And there are multiple choices for, let's say, the TFM. So if I search for it further down, these are kind of the feature transformers. So we have just a few: normalizer, min-max scaler, robust scaler, standard scaler, and PCA. So that's it. And then in terms of the estimator, we have logistic regression from sklearn, decision tree, random forest, gradient boosting, extra trees classifier, Gaussian, and K neighbors classifier, and QDA. So that's essentially the entire space. Again, it's a small subset, but enough for this particular exercise. So I should mention two things here. While this grammar was manually created by people, you can imagine an automated process. We don't have it in this exercise, but you can imagine an automated process that goes to sklearn and just uses the class structure to kind of figure out some of these elements, right? Which are the feature transformers, what are the subtypes of feature transformers, what are the estimators, what are they applicable to, and so on and so forth. In this case, we derived it manually because this was a special use case, but I wanted to say that it is possible to derive such a grammar automatically, although, you know, the expert's knowledge with respect to what combinations work and don't would be very useful in this space. So you might want to generate automatically, but you might want to moderate it with kind of human input. That being said, the next thing I'm going to do, and I'm going to open the chat window again, just so I can see messages. The next thing we're going to do is we're going to translate this to an HTN domain and the domain definition and problem. So we're going to take that form and translate it into an HTN. And if you're familiar with HTN, they have the same hierarchical structure that this type of an expression of a grammar has. So it's kind of a natural match. I'm just going to press Ctrl Enter here, and it's created two files, which I'm going to look at next. So it created domain HTN and problem HTN. And we get some benefits from, you know, the PDDL plugin highlighting this stuff. But what you're going to see here, remember I talked about I talked about maintenance actions. Essentially, what you're going to see here is every sub non-terminal of the grammar is now a method. Sorry, so each of these will have its own method, each choice, you know, each subterminal. Sorry about that. Made the change. So you're going to need to have a lot of maintenance actions to understand where exactly are you in that sequence of actions from within each method. So that's exactly what this does. It generates, you know, a bunch of a bunch of maintenance method, as well as, so again, we have methods for the various cases for estimators, but ultimately, you know, you will ultimately get down to some actual actions which corresponds to some of our primitives in sklearn. So you can probably recognize the names there. So I just got into the actions. So it's a relatively simple translation because, again, the grammar corresponds to the HTN, but you get the idea. Now, at this point, we don't really have a goal. The goal is empty. The goal will be filled in later, and I'm going to get to that in the tutorial. But just for fun, I also generated I apologize about that. Wrong line. I also generated a kind of a visual depiction of the grammar, so you kind of get an idea of what this looks like. So this is the DAG, and then you have this choice, or you have that choice followed by DAG, or you have, you know, one of these followed by, with that DAG in parallel, followed by a concat, or you have a bunch of the estimators with a DAG in parallel followed by a concat, and then there's an estimator at the end. So the grammar is kind of self-recursive, obviously, but so you can get many possible combinations. All right. Again, stop me at any time with questions, please. I'll be happy to answer them when I get to them. So I'm going to get to section 3, which is all about why really do we need planning? And this is reason 1. So you might argue, for instance, that I'm running this cell. You might argue that I can just take the grammar and just generate strings from that grammar. And the strings from that grammar will essentially be pipelines at the end of this workflow. They will be pipelines for my ML flows that match the grammar. So why do I need planning at all? Well, the reason I do need planning is twofold, but the first reason is I often need constraints in this space. So for instance, I want I know that I have a feature somewhere that really requires a particular type of transformer, say PCA. So then I want to make sure that PCA is in the flow. And that is typically very hard to do if you're just blindly enumerating variants of the grammar. As a matter of fact, Lale itself, the library that allows you to write these pipeline expressions, does have an option of creating branches that have choices in them. So you can say A or B or C on a specific branch, and then it has the option of starting to enumerate blindly from those options to kind of give you one grounded pipeline. But if you want constraints in that, then it does not have a function for searching for things that have specific constraints in there. So as an example of that is, I'm just going to pick 30 pipelines here for starters, and then I'm going to go back on this cell. I'll tell you why in a second. But let's say I want to have something put concat because I want to have a more complex graph, and I want to have something with PCA, and I think it was, what was I doing here? Okay, there we go. So concat and PCA. So I'm going to generate the PDDL descriptions, and I'll show you those in a second. But the one thing I wanted to show you was, and I'm running this cells, by the way. I just ran a planner, but I'm going to go back on this cells and explain them in more detail. But the one thing I wanted to show you was what they look like, and Lale allows me to do that by giving me these displays. So let's take a more complex one. So this runs QDA and it runs PCA, and then it concatenates those features, and it basically applies logistic regression afterwards. So the way these pipelines work in Lale right now, in this particular example, is they apply a particular transformer to all the columns in your data set whose type that transformer is applicable to. So if it's a certain positive, it's only positive numbers, you can run certain transformers. If it's numbers in general, you can run other transformers and so on. So it creates basically a derived set of features, and then you can append multiple sets of features to kind of the final result that feeds into training your estimate. So this is what the various pipelines that we just generated look like. And they're pretty simple because I only chose 30. So even with 30, I have a lot of possible combinations. Typically in a typical run, you choose hundreds, maybe 1,000. But right here, for the purposes of this example, we're going to choose just a few. The reason I did this was to show you that constraints are helpful in these cases. But I'm going to go back and actually run through a tutorial with a much simple goal. And that is, I'm just going to run tape pipelines. And the reason for this, we're going to use hyperop to do hyperparameter optimization. And I want to do it live, and I don't want it lasting forever. So I'm just going to choose 10 and PCA. And I'm going to generate PDDL again. And let's look a little bit at the PDDL. So right now, I should have a domain PDDL and problem PDDL. And we have a JSON file from the call to the planner, but we're going to redo that in a second. So these use the HDN to PDDL translation by Alford et al. To basically generate PDDL problems. So at this point, we actually have a goal. I'll show you that in a second. So you might notice some of the predicates which are kind of derived from the HDN problem. And some of the arguments are basically trying to maintain the structure of the HDN and encode it into just plain PDDL. That's essentially what this translator does. I really invite you to read their paper. It's very, very interesting. But HDN has a certain structure about how a problem gets decomposed. And essentially, they're just trying to translate those constraints into PDDL, constraints expressible in PDDL. So you're going to get a lot of actions like this, where you're going to get stuff for opening a bracket or closing a bracket and things like that. And you're going to get all sorts of preconditions and defects that have to do with enforcing the structure of the HDN, but in PDDL. You're also going to get something else. So for every particular primitive or every part of the original grammar, minus those strings, those kind of syntactic artifacts, we assign a cost to each action. So Michael already has gone through this, but each action in PDDL can have costs. And remember, lower cost is better. So lower cost actions are preferred. And the cost of the total plan is the sum of the cost of the actions in that plan. So it's very, very simple arithmetic. And in this case, at this point, we don't know anything about how good these particular sklearn classes are, the transformers and estimators. So we just assign we decided on cost for this example between 0 and 100, and we just assigned 50 for just this example. So you're going to see that a bunch of things have cost 50 in your domain. And that's going to change as we move towards the end of the tutorial. And it's going to change in a principled way based on what we see by applying these to data. Let me go to the problem as well. So the problem, the goal at this problem, at this point, is just that I have PCA in there. So remember, I selected PCA. So because I selected PCA, there is only one goal at this point, and that is, well, one of it is you have to complete the obviously the structure, and that's part of the translation of the HTN to the PBDL. But the other part of it is we have to have PCA in there, right? So that's part of the goal. So let's actually run a planner on that in the tutorial. So I'm going back to my original notebook. I'm just going to run this cell. And this cell runs the K-star planner. So in case you're not familiar with these, K-star is a top K planner that we developed in IBM, but it is open source, so you can download it from the links that I put on this exercise. It's essentially conceptually similar to A-star, but it does maintain the top K paths rather than just the most promising path. And that's essentially the crux of it. You can read our papers on it. But we developed it in IBM, and it's very useful for finding the top K optimal plans according to your optimization criteria. And in this case, the optimization criteria is cost. So remember, the cost of the plan is the total cost of the action. Now, since everything is equal, but the syntactic operations, open parenthesis, close parenthesis, the shortest plans will win because they have the shortest total cost. So if I have PCA in there and something else, then my total cost will be a little over 100, right? 50 for PCA, 50 for an estimator, and then a little bit of a cost like 1 for each syntactic element in there. So at this point, we know nothing about how relatively good these particular sklearn components are one from the other. So we're just gonna return short plans. That's why initially I did this additional constraint thing and asked for 30 plans, so you can see slightly longer plans. No, they weren't very long, but they were slightly longer than I would get in this instance. Before I show you what the plan JSON actually look like, you might actually notice that this is a command, and we run this command. I'm just going to go to the terminal and just run it. Right, so this just ran the K-star planner, and the reason I was able to run it so easily, I have plan utils installed, and all of this is in the instructions, and I did plan utils install K-star. So I have K-star available, and all we did is essentially generate these PDDLs in a temporary location, other than output, just so we can run it in temp for situations where you have clustered file systems, where you have distributed file systems. It gets a little complicated. So we like to write to temp, at least temporary results. And essentially it just dumps this result to JSON, and it asks for 50 plans. Why do we ask for 50 plans instead of 10? Remember, I asked for 10 plans. Because sometimes we're gonna get distinct plans who produce equivalent pipelines, whose only difference lies in which path did they take to produce PCA followed by some estimator. So you may have multiple paths in that grammar decomposition to basically achieve the same pipeline. And for the planner, those are separate plans. But for us, they're not different pipelines. So we really want 10 pipelines and not 10 plans. So therefore, we typically ask for a larger number of plans than we actually need, because some of these will not be unique, will not produce unique pipelines, just as an explanation. And we are dumping this result JSON. And then we're basically writing that output to this first planner called JSON. I'm going to show you that in a sec. So so again, we have the result JSON because I just ran it from the command line. But essentially, this is it. So you get the plans, and the plans are sequences of actions. right? Sequences of actions from my original PDDL. And they have a cost. So as I said, it's a little bit over 100 because there are some strings in there, syntactic artifacts. But essentially, most of them are like two-step pipelines. And you're going to see some probably lower in the file that are three-step pipelines. You can guess by how large the cost is at this point, right? Because remember, the core sklearn things have a cost of 50, and everything else has a kind of a minor cost. But you see that these plans aren't really pipelines yet, right? They have a lot of syntactic artifacts in there. So I know there's a normalizer in here, right? And I know there's a PCA in here because I asked for it. And I know there's a decision tree classifier in here just by looking at it, but it's not a pipeline yet. I can't really run this in a meaningful way, right? So part of the code that we wrote, and again, I was talking about that at the beginning, is the transformation of the area application domain into a planning domain, and then the planning results back to your application domain. So how do the next step for us is essentially to post-process these plans, and we know all the strings that were matched to specific things in the grammar, and we know if those things in the grammar are actually sklearn primitives or they're syntactic artifacts. So at this point, we're just going to reconstruct the string that the grammar wants based on the sequence of actions in this plan. And that's exactly what's going to happen next in the tutorial. For each plan, we're going to take the sequence of actions, and we're going to construct a string. And that string is interpretable by Lale as a pipeline. So let me show you that. And this is what I did earlier, but I jumped over it very, very quickly. This is essentially this block that displays them in a nice format. So this is the actual string that Lale can interpret, right? And if you have things like concats and so on, you can play with those, and you're going to see that the strings look a little bit different. So there is an operator overloaded for kind of parallel branches, and there is an operator overloaded for a fan in and a concat and so on. But essentially, it's going to be a string that looks a little bit like this, right? And this is the original string that matches this is a string that matches the original grammar. And I got 10 of these because I just, from the 50, I started transforming them into pipelines all the way until I reached 10 unique pipelines, and then I stopped. But remember, we got 50 plans. So in the JSON file that you're going to look at, this one that I just showed you, you're going to get way more plans than the original 10 because we asked for more. How many more should you ask for? It's really a domain-specific problem. We typically ask for at least 50, and most of the time kind of 1.5 times the number of unique outputs that you want, but this is just our particular experience. So the one thing that's nice that Lale does, it displays a little graph with what the pipeline looks like. And this is what we're doing in this cell. All right, let me stop here for just one moment and ask any questions before we start doing optimization and cost restructuring of the pipelines. Okay, going once, going twice. All right, I'm going to move on. But again, please interrupt me at any point. What we're going to do in the next section, we're going to take one pipeline, the first one, and run hyperparameter optimization on a very small data set. The iris, the infamous, I should say, iris data set. And just to show you how that's done. So now that I have a pipeline as a kind of an object that Lale understands, I can actually set up a hyperopt instance for that pipeline as an estimator. So I choose the pipeline with index 0, so the first pipeline, but we can change this as you want. And then I'm just going to show it just so you see what it is. So PCA followed by logistic regression. And then in this cell, we're setting up a hyperopt instance. It's going to do 20 evaluations, and it's going to score based on accuracy. And it's going to use this pipeline. This is the particular attribute that corresponds to the Lale object in this structure. It's going to use this particular pipeline as the estimator. And then we're just going to initially just load the iris dataset. And in case you're not familiar with it, very simple one. You have species. I don't remember exactly how many there were, but they're numeric, 0, 1, 2. And then you have 4 features, sepal length, sepal width, petal length, petal width, and you're trying to predict the species based on the numbers for those features. Right? So I just printed the first 4 rows in that data frame. And now what we're doing in the next cell, it's essentially we're calling fit for hyperop. So we got the pipeline, but what we want now is a trained pipeline. We want a pipeline that doesn't work on its default parameter settings, but on the best parameter settings for this particular data set, for this particular problem, for this particular domain. Sorry. So in doing that, we're going to compute the accuracy score, and then we're going to use that trained pipeline to predict on a test set that we split from the original data set. So if you look here, we have a test size of 0.2. So about 20% of the original data set is our test set, and we're going to use that trained pipeline to predict based on that. So standard machine learning stuff. But again, we used plans to get to the pipelines up to this point. So theoretically, given the grammar, no data scientist need be involved up to this point, except that now I'm kind of doing it on a one-off basis. So, so we're gonna run this for a little bit, and as you see, the loss changes over time, and then it displays the prediction. And it's not perfect. You're gonna see a couple of species, if I remember, that are not predicted correctly, but most everything is. Just scrolling down, I think there were a few misses. So for instance, this one is a miss. This is the predicted, and this is the actual. And but most of them, this is a very simple data set that most estimators will work very well on. But we did this for kind of one pipeline. So we trained it for the best parameter settings for this particular data set. And you're free to do this for any data set that you choose. Right? But we did that for just one pipeline. And while that's okay, that's not very, very interesting. So what I'm going to do next is I'm going to initiate the same process, but on all the pipelines that the planner returned. And remember, I just did 10 because I wanted this to go really, really fast. But in the meantime, I'm going to talk about what's going to happen next while this trains. So let me start it. This is going to start going through the plan. So in this case, it's a plan 1, and it's going to train that, and then plan 2, and so on. Typically, we do this for, as I said, hundreds or thousands, but obviously we didn't have the time here to do it for hundreds. But I wanted, while this is going on, to just talk about what's going on next. So remember, I talked about those costs. Like we gave everything a cost of 50. Right? Because we didn't know which particular combinations or which particular individual sklearn classes were better than others for this particular data set or this particular domain. And what I want to do next is use this data after we train the parameters and we run the prediction problems on the test set, and we can evaluate on the test set how well each particular plan or each particular pipeline has done. We want to be able to use that data to change the planning domain so that the next time we run it, we get better pipelines according to that metric. How do we do that? Well, in this particular tutorial, we took a very, very simple assumption, and I'm going to state it right now. And of course, you can change it for your particular use case, which is a pipeline's accuracy is formed of a number of contributions. So the elements of the pipeline contribute to how good that pipeline is, how high its accuracy is. We took the simplifying assumption that every element, every class, every feature transformer estimator contributes equally to the accuracy of that pipeline. So that's the simplifying assumptions we take here. And obviously that's not true in every case, or in most cases maybe for different domains. But even with this simplifying assumption, I'm going to show you after the tutorial is over that we got some pretty good results where we match expert accuracy for a wider number of problems. So that is the assumption that we took. Now, given that assumption, and given the fact that you know what the accuracy of each pipeline is, and what how many times each particular sklearn element appeared in which pipeline, you can imagine that there is a very simple arithmetic formula to kind of compute an individual score for each sklearn class in terms of its contribution to the accuracy of the pipelines that are listed. I'm going to show that in the next cell as soon as training is over. Let's see where it got to. Okay, so there we go. So we went through 10 plans. And in the next one, I'm going to show you the pipeline accuracy. Right. So what I get on the left is one thing I wanted to tell you, by the way. Lale kind of also produces this kind of importable pieces of Python that you can just use evalon and just run. And essentially, it basically gives you the trained pipeline with the best kind of parameters. So what type of scoring and so on and so forth. So these are kind of the different accuracies after kind of 20 rounds of training. So again, we're doing a kind of a toy job, but just so you can follow along in less than an hour. It's for demonstration purposes. So these are the different pipeline accuracies. So they're very high. Why? This data set is very, very simple. As I said, it's still on the iris data set. It's very, very high, but some are still better than others. So for instance, like this one that uses a Gaussian, it's not as good as this one that uses logistic regression. And actually, it's not nearly as good as the one that I think uses the KNN, right? So this one is one. Now remember, each one of them has PCA because I posed that as a constraint. So everything has to have a PCA in it. So some are better than others. Now, based on that, I can now compute using some very simple arithmetic, and you can check our code for it. What is the cost that I should now assign to each sklearn element in order for them to kind of match their contributions to these accuracies? So for instance, PCA appears in everything. So I don't expect it to change much. I expect it to be kind of middle of the road, like 70 is fine. But K neighbors classifier, for instance, this did pretty well. So I expect its cost to be lower. So remember, lower costs are better. Whereas the Gaussian, which did pretty badly, I expect its cost to be higher. And again, this, because everything has PCA, PCA is not that important. But remember, some pipelines may have multiple other elements other than PCA, like this one, for instance. And in that case, we're going to count how many times did logistic regression appear, then compute kind of a weighted contribution to the accuracy scores for each single scalar component. And if I run the next one, this is what it is, rounded. So PCA is 75, 76. K neighbors classifier is the lowest, it's 50. So it maintains its kind of original cost. Gradient boosting classifier is 50, probably because I didn't see it in the original data set. So you can take optimistic or pessimistic assumptions, or maybe I did see it, then it did well, I don't remember. But some of the ones that are Gaussian, for instance, have really high costs, right? So I boosted up the costs significantly because I saw that they were not doing that well relatively to others. So what we can do now is regenerate the domain, and what we're gonna do is regenerate the domain and problem PDDLs with a new costs and rerun the planner and see what the top 10 were in the old iteration and what the top 10 are in the new iteration, right? So let's do that. Well, it didn't display my table. I'm not sure why. But okay, but I got an error, but at the very end, I'm not sure why it's not displaying my table. But let me just show you the plans. I think that might be more useful. So I'm going to close some of these just to clarify this. So I'm going to look at the original domain and the domain after feedback. So let's take something like, so we talked about, let's take one of the, sorry about that. I made a change. Let's talk about the Gaussian, right? So the original Gaussian and I'm going to try to find its cost at an initial cost of 50. And in the PDDL afterwards, I'm going to search for the same thing. And it now has a cost of 101. So normally the plans with a Gaussian are going to be not as good as the plans without the Gaussian. So to see that, what we're going to look is that the results for the first planar call. I'm going to go all the way to the top. So this is the original one that we did very early on in the tutorial. And this is the second one. Oh, something happened to the, oh, there was a failure of the planner. Let's see what's going on. Okay, I apologize for that. I'm not sure what happened. Let me run it in the command line and see what happens. And we're going to try to debug that here, but if it doesn't work, then I'm going to have to. Okay, it says enough solutions found. I'm guessing I should have a result JSON here, but I don't. Okay, we're going to have to debug that. I apologize about it. I'm not sure what happened. But what we should have seen here is, did I run all the cells? Maybe I didn't run all the cells. I'm not sure. Let's see. Yeah, we're gonna have to figure out what went wrong there. I'm not exactly sure. What you should have seen here is the table that compare the two. I think I might have saved a screenshot of that at some point. I can add it to the presentations later. But essentially, in the new version of things, the plans with the that used to contain Gaussian are much deprecated, and the plans that now contain k nearest neighbors are further up in the hierarchy. So they would be among the top plans in the hierarchy. I'm trying to see if I ran all the cells correctly, just to make sure. What I'm gonna do is I'm gonna continue with a few slides, and what I'm gonna do is I'm maybe gonna run this again. Let's just restart this. And I'm gonna run it all the way up to here. And let's see. I'm gonna just run it again just in case something happened that I wasn't planning on, and see if I can get those results by the end. And now I'm just gonna run everything up to here. And let's hope that this is now running. Oh, sorry about that.
Octavian, I have a screen that shows the two comparison. Do you want me to share my screen very briefly?
Yeah, absolutely. Do
Okay.
that while I do this, and then I will. I'm gonna stop sharing, and then I'll go back to my slides.
Yes.
Yep.
Do you see that?
So there it is. Yep. Perfect. Thank you, Sharon. So this is what was supposed to happen. I'm not sure why it didn't, but I'm going to debug after this. So this is exactly the same example, but in this particular one, you see the first iteration is what we kind of got the first time when we didn't know anything about each particular sklearn component. And then on the right, you get this after the feedback, which is after we ran the hyperopt, and we trained, and we ran it on the test set, and we computed the accuracies, and we recomputed the cost of every action. So again, the k nearest neighbors classifier is on top, everything, the Gaussian is very far to the bottom, and everything else in between is according to their particular costs. So this is what I expected to see, and I'm not sure why mine didn't work right now. But this should, thanks Sharon for finding this. I am gonna pause there for just 1 second and see if there are any questions. And if not, I'm gonna go back to my slides for just a couple more things. Any other questions? Okay, let me share my screen again. So I hope you can see my screen again.
Yes, we can.
Okay, thank you, Shin. So if you take this and kind of turn it into a realistic application, where we actually do this for way more pipelines and the larger subset of sklearn and opens and data sets from OpenML. So we only shown in this picture these data sets with the accuracy of under 95%. But we did in this case, we actually we had experts manually craft some chains. And this chains although they were short, like 2 or 3 elements, they had a lot of choices in them. So each branch had a lot of choices in between feature transformers and estimators and so on. So they were actually pretty rich. The space of possible choices was fairly large even for them, even for the ones chosen by experts. So with that in mind, the one thing we were looking for is, can we match the accuracy of human expert crafted pipelines without having them crafted? And the answer is on almost every data set, yes. And on a lot of the data sets, we can get there sooner. Meaning, if you take the time to train these LaLe pipelines that have choices, HyperOpt will essentially start optimizing between those choices as well. So it will try to pick the choices that are better. So if you just measure that time versus the time of doing this process of training pipelines, getting the feedback, and then changing that to scores, to costs for the planning actions, and then getting new pipelines and then training them again and again and again and again, either in rounds of 50 or just one shot get 1,000 plans and just hyper train the parameters for them. In almost all the cases, we can match human accuracy. And in a lot of cases, we can get there earlier. So in these cases where the red and yellow gets to kind of higher accuracies earlier than what we could do for the large, very choice intensive pipelines that people create. So we weren't looking at that point to surpass them, at least not on these data sets where the accuracy is very, very high anyway. But we thought it was a very meaningful result. So there's a publication on this, which is in our references, and you're free to check it out. So that's kind of the realistic version of this. I kind of shown you the toy example of this in terms of what we went through the tutorial step by step. So with that, I'm gonna move to, unless there are other questions, I'm gonna move to 2 things. Yeah, so the demonstration effect is that I actually got mine to run while I was talking. So there you are. I don't know what happened exactly, probably some, I forgot to run a cell appropriately or something like that, but I ran everything from the beginning. And you can see kind of what Shirin showed you, but live. Let me rerun this cell. Yeah, so this is the table that you should expect. So that's kind of what happened in the tutorial. Just one iteration of that loop. Now as homework, what anybody could do is automate that and run 50 iterations, right? Plan, train, compute the accuracy on a test set, reflect that into scores, into costs, pre-plan, and so on and so forth 50 times and see how good your pipelines are, essentially. So I'm going to go back to the tools and I wanted to pause just for a second, and then I'm going to talk about a few other applications where we found this kind of transformations from a domain that doesn't appear to be planning to a planning domain very useful. Any questions on chat or anywhere else? See chat. No. Okay. All right. So let's go to a couple more applications, and I have a couple of slides to conclude and hopefully some more discussion. One thing that this application with ML pipelines was inspired from was something we did much earlier, which we call the automated analytics composer. And essentially the idea behind it was, especially with IBM, a lot of these middleware companies sell very complex systems that are very difficult to program by your non-experts, right? So if our streaming platforms, our MapReduce platforms. Yes, hi, Josefina. Thank you for the question. I'm gonna answer that in a second, if you don't mind. So with a lot of these analytics or components, they're kind of very difficult to write programs for, put together by non-experts. So what we decided to do is to put that power in the hands of experts, in the hands of domain experts rather than programming experts. So, you know, your business analyst has a certain data processing goal. They want to be able to express it. And based on that, they want various components to be put together automatically, whether they're streaming, whether they're at rest, and then process some data in a certain way and get them a result. And this was done. We created an interface for this. We had demos at AAAI, ICAPS, and so on a number of years ago. And this was kind of the first iteration of this idea that the pipelines are going to be created. Automatically. So now there is a question on the chat. Could you explain preconditions and defects that distinguish different sklearn components? In this case, there are no preconditions or defects. Anything can be applicable to everything, except that, because remember, the different transformers are applied en masse to every column in the data set whose data type allows it. So that's the way Lale interprets these pipelines currently, if you write it in the way in which we wrote them. There is a constraint in the grammar that every flow ends with an estimator. Every pipeline ends with an estimator. So that's the primary constraint. Other than that, any other constraint that the user wants. So during the tutorial, I kind of selected certain components. Essentially, at that point means I want this component in the flow. You can design more complex UIs that express more complex constraints. Like I want this particular component at the beginning of the flow. And all of those are imposable in some way over the planning problem. You can find a way to do it, I'm sure. But right now, any combination that matches the grammar is possible. Is this idea directly transferable to neural architecture search? No, there's nothing that speaks against applying the idea to NAS. If you see the kind of a different layers and architectures as components, you can essentially design any kind of anything that resembles a data flow, a forward flow, right? There are problems with creating graphs that have loops sometimes, but we solve that as well, or we have a solution for that as well in our scenario planning approach, where we do sometimes create graphs that have loops. Related to neural architecture search, there's nothing that prevents you from doing it. The only thing I can think of is it might be very, very expensive from an energy standpoint to create a lot of these combinations, some of which, so remember, planning searches somewhat blindly unless you give it kind of a domain that can guide it, right? So you can find all sorts of combinations that make no sense, but training those over GPUs will take a lot of energy. So that's the only constraint I could think of, right? That you're going to waste a lot of energy training things that don't make sense. So you have to be careful with how you specify your original grammar or your domain or your, the constraints for how the different layers are combined. Yep. Thanks, Boris. Next one. So this application that I just described, the ML pipeline, was actually part of a larger project within IBM that was combining this idea of kind of automating the creation and the evaluation of pipelines with the idea that you can do performance evaluation on benchmark data sets on a lot of these components and combinations. And if you have all that data, that's excellent data for an initial very good set of planning action costs, right? So you feed the planning action costs that come from this thing we were calling the analytics scout, and you feed the approach that uses planning to generate new pipelines into this composer, and then that will essentially give you other data science pipelines that might surprise you, that people haven't thought about, that might be applicable. And the choice of these, the ranking of these, will be informed by how well the particular combinations or the particular individual components do for particular data sets, and how similar that data set is to your problem that you're looking at. So that's kind of the larger picture of the real world application, if you wish. I wanted to come back a little bit to this one. There was a question about it earlier about who's the agent, right? So if you remember, Shirin showed you a healthcare application where you would see the patient transition through states, and there's a question about who's the agent, and is it the virus or the infection, or is it I think God was mentioned, and there were a lot of other possibilities. We had an actual very similar application. The actual original application for which we built this hypothesis exploration was malware. So if you look at malware, and specifically we wanted to hypothesize about which machines on our network were infected with malware. And we saw as a definite confirmation of that, if one of these machines would try to contact the command and control machine, that's one of these blacklists maintained by Google and other companies of machines that are command and control centers for malware. So in that situation, we are seeing a set of observations like executable downloadables, it contacted various networks and so on, at the very high semantic levels, things that you see in these bubbles. And we wanted to figure out what is this machine doing, right? So there are a few normal behaviors, a few normal state transitions, and there are a few abnormal state transitions, like, malware has been activated on this machine and so on. But some of the valid things actually are ambiguously look like the invalid thing. So for instance, machines that crawl. And in the IBM research network, there are a bunch of these for various purposes. And sometimes the observations are the same. So it's at this point for us, it wasn't important whether there is an actual agent making a decision, whether there is a program that has been programmed to make a choice between A or B or C, depending on its circumstances, or whether we simply cannot observe everything, and therefore all we really see is a set of possible variants, a possible choice, a set of possible states following a set of other possible states. So put in the position of the observer, where we need to diagnose what's going on, we turn this into a plan recognition problem. Like, you get a set of observations, this bubble that you see in this diagram, and essentially you want to infer the set of states that happen on the top. And the reason, of course, you can do this with statistical methods. You can do this with Markov type methods. However, the probabilities of these transitions are very, very hard to derive in practice, and very hard to obtain from experts either. Both in the ICU setting and in the malware setting, we try to do that, and it's not really feasible, right? So really what we resorted to is just allowing them to tell us what the transitions are, and then solving for this problem by generating many, many, many possible plans. And among those possible plans, you can think of that as a universe of possible worlds, and you can actually compute probabilities about what is actually the case. But more importantly than that, you can preposition yourself to make certain observations. Like, if you expect that you're in case 1 and a certain other observation will follow, then you can monitor for that specific thing. Will this machine send an email to a domain that ends with a specific terminator? Right? And if that's the case, then you have confirmation that one of the hypotheses is happening as opposed to the others. And the situation is almost exactly the same in the ICU case, where you do tests to determine is this patient in state 1 or state 2. Right? Finally, Scenario Planning Advisor was kind of the crowning achievement of all this work, where we put a lot of things together, including the ability to derive some of these symbolic models automatically from text, the ability to derive multiple plans, multiple paths to that graph, kind of causal effects in the semantic sense of causal, not in the probabilistic sense of causal, and then put them together in a kind of something meaningful for users. And Chin kind of gave you some idea of what that is. And that is it for that deck of mine. I don't know if can you see these slides?
Yes, yes, we can.
All right. So before I go to summary, I'm going to wait for another couple of seconds for any questions. And I have 2 more slides and that's it. And I'll be really, really fast. Okay. So what did we see today? Hopefully you saw an introduction to AI planning. You know what it is, how it works, why it's important, large state spaces, search through them with a kind of a meaningful goal to achieve. You've seen a little bit on the planning theory. Just, Michael gave you a very concise but very pointed introduction so that you can do useful things with it. Formalism, models, languages, algorithms. You've seen some example of applications where modeling is crucial, and I think that's a kind of an unrepresented maybe not somewhat anymore, but when I started all of this work, it was a little bit unrepresented in the planning community, how important finding the right and a modeling approach for a real world problem is. And finally, I gave you kind of a walkthrough on this ML pipeline exploration case, one that you can run separately at home. And you can then take it further by doing what I did in one iteration of the loop automatically through multiple iterations. So good news and bad news. Good news is we can solve really, really hard problems. So just as an example of these results I was talking about, the ML pipeline exploration, the real application we published in ICAPS 2020. In terms of hypothesis generation, that malware problem that I just showed you, we actually had some very good results where we could predict when a machine will contact a blacklisted domain about 8 hours in advance, just from its behavior, right? Based on the network. And with scenario planning, I think Shane gave you the gist of it, but we're much, much faster than any human could pass, or a team of humans could possibly be. So we can solve really, really hard problems. There are some things that we can work on, right? In the growth mentality, first of all, expressing problems in a formal planning language is a definite barrier. As Shane said, experts are not readily available. And there are a few knowledge engineering tools to assist users, but they're kind of far and few in between. So we have these transformations from a certain application domain to the planning domain that we did kind of over and over. We saw over and over in our careers in building applications. And right now, there's no good way to kind of share those and reuse those. So that's an issue. And we don't really have development tools that go end to end. So what you saw today was kind of a combination of multiple open source tools that I put together just to walk you through an example, right? But it's not ideal for most production scenarios. The other thing that we saw over and over is multiple plans. But I believe that the community is now somewhat convinced of this, right? Initially, when we started, I mean, most people are focusing on finding the cost optimal plan. But in reality, you're never going to be able to express all the constraints you want in the planning domain. So given that the fact that the planning domain is going to be incomplete, you do want multiple plans. It's the same reason why you want multiple routes on Google Maps between you and the airport, right? Because there are things in your head about which route is better at certain times of day, or which bridge you hate taking, or things like that are not easily expressed in your search. So getting multiple plans in most practical problems is the key. And if you can do the top K, then that's even better because you have an optimal criteria and you can justify why you picked the first 5. Now, AI planning is faster to prototype typically than domain solutions. So for instance, we had the malware problem. We could have built a custom solution just around that. But using AI planning, transforming into AI planning, it was faster to get into a prototype. But we still need faster prototyping because of these problems of the formal planning language. Expressing that in the formal planning language is a little bit of a barrier. And having these experimentation frameworks, things like a Jupyter notebook for planners, right, where you can play around with your domain and the problem and so on and see multiple results and outputs. So we still need faster prototyping tools. And that's it. Those are our conclusions. We hope you enjoy the tutorial, and we welcome any further discussion. Shane, I think you can stop recording now. Maybe there will be